All right. Hello, everyone, and welcome to another live stream. So it's going to be another one kind of focused on some specific Incus feature more than anything else, and just trying to make things a bit better. I think today's topic is probably one that many people have never really thought about or dealt with before, which is NUMA. And for anyone who didn't look it up already, NUMA stands for Non-Uniform Memory Access, and it's primarily something used on systems with multiple CPUs. So for most people, that means dual socket, quad socket servers, and all of the complexity that comes with that. It also applies to some other more consumer grade-ish systems. So at least the first generation of I think it was just the first generation of the AMD Threadrippers also were using NUMA within a single socket. That's because the first generation of AMD EPICs, as well as their workstation counterparts, so the Threadrippers, that first generation effectively had every one of the CCDs, so those dies, those chiplets effectively act as its own NUMA node. So even though you had a single socket, you effectively had 4 NUMA nodes. And that's something that's technically still true to this day with the newer chips they've made, except that this is now being completely hidden away effectively by the firmware. I believe there is still a firmware option to expose that. So even on a single socket AMD EPIC, you could turn that back to seeing anywhere from like 2 to 8 different nodes. But normally it's not really a thing. The other place where I expect NUMA could actually be used, but I don't know if it is or if they're doing something else, would be on phones. Because the vast majority of phones use a ARM design called Big Little, where you actually have two, I think even these days maybe up to 3 different CPUs that each provide a number of cores, and they've got different characteristics. The big cores are much faster, higher performance. The little cores are much slower, lower performance. If this is all done within one chip, maybe they can abstract it somehow that way. If it's done over 2 different chips, then it's quite possible they actually do use NUMA for that, to actually represent the fact that you've got 2 different CPUs, and that things like memory access coming from the little core, accessing the memory attached to the big core, that needs to go through a hop, and therefore has some amount of performance like slowdown and issues coming from that. So yeah, that's basically what NUMA is designed to encode. It's a way to report all of the CPUs you have, all of the memory banks that you have, and giving you an idea of the cost of accessing memory from a given CPU. Like again, for most folks who may not know that, typically on most systems these days, memory is effectively directly driven by memory controller within the CPU. So in a server with 2 or 4 sockets, the memory banks are effectively split between those different CPUs. So when you put your memory in, you're supposed to put 50% of your memory, well, say you've got 2 sockets, 50% of your memory on socket 1, 50% of the memory on socket 2. You don't strictly need to. You can actually misbalance on purpose if you want to, in some cases. But yeah, effectively you've got some chunk of memory that's directly wired to one CPU or to the other. That doesn't mean that the second CPU can't access memory that's held by the first one. It just means to do that, it needs to go through an internal bus from one CPU to the other and then to the memory, which comes with extra cost. All of that gets even worse when you start considering newer technologies like CXL these days, which effectively turns NUMA from an in-chassis thing to an out-of-chassis thing, where you could technically access memory that's attached, that's either like part of a PCI device type thing, or that's in an enclosure outside of the server, or is even on another server in the rack. And doing that comes with like more and more hops and costs effectively as you're dealing with that. So yeah, that's definitely pretty interesting. There's also a bunch of crazier kind of NUMA topologies that are possible with things like mainframes and that kind of stuff. Anyways, for today, we're going to keep it simple. So it's just going to be looking at a server in my lab here, which is a dual socket. It's pretty low specs, actually some old hardware I had kicking around that I'm using on this machine. So if we look at LS CPU, we'll see they're Intel Xeons E5 2620s V2. So they're each 6 cores with 2 threads per core, and there are 2 sockets. So that means in total we've got 24 threads that are available, which is what's showed here as being online 0 through 23. And I do have Incus installed but not initialized yet, so might as well go through that. I'm just gonna do a quick init. What can we do? I can do BRFS. Actually, let me just make sure I've got the ZFS tools installed and just use that. And I guess the other thing I didn't touch on is the other thing that's typically directly attached to one CPU or the other are PCI lanes. So your PCI devices are also effectively tied to a NUMA node. And the same goes if you're doing GPU pass-through or network pass-through, that kind of stuff, and you're giving that to a VM or a container that is on the wrong NUMA node, then every single kind of access is going to come with a cost. So that's another aspect I need to keep in mind. All right, so I should have what I need to do an init here. Okay, not sure why it's still not seeing ZFS. For what I'm doing today, I could use anything else really, but I'm just gonna use to it. Okay, there we go. It's because it did exit on startup and therefore didn't actually do anything. Okay, so I'm just gonna pick the default for everything, and here we go. So now that we've got Incus, let's look at the report of resources according to Incus itself. And it does report all of that stuff for us conveniently. So again, if we look at CPUs, it sees the CPU, it shows per socket. So this is socket 0. So that's the first of the 2 sockets. It shows it's got 6 different cores, and each core has 2 threads. And we get the CPU IDs. One thing that's always a bit confusing to folks is that they often expect things to be sequential, and they're really not. Cores, in this case, cores 1 through 6 are gonna be ID 0 through 5, but then their threads are not gonna be 6 through 11 as one would expect. They're gonna be 12 through 17. So just need to keep in mind, and that's a normal pattern. That's what you usually see. So you just need to keep that in mind. If you actually wanted to pass that whole CPU to a VM and you just type in 0 through 12, you're not doing what you actually think you're doing. You're passing the first 6 cores of each of the 2 CPUs, which is pretty much the worst thing you can do as far as passing things to a VM, for example. So it also shows that for all of those, the NUMA node is 0. So we can see that here. And then we get the second CPU, which is the same deal, but this time we see it's got its cores at IDs 6 through 11, and it's got its threads at IDs 18 through 23. Okay, and we do see NUMA node 1. Now, on the memory side, we also do show the NUMA nodes. So total memory in this machine, it's just got 128 gigs of RAM. And we can see that this is split pretty much evenly at 64 gigs per core. I mean, actually extremely evenly. There's always a bit of a inaccuracy with some of that stuff because the firmware does reserve some memory. It will usually take that from the first NUMA node, not from the second one. So there's some fun going on there. And then comes the rest. So GPUs, again, shows you what NUMA node it's on. And then same thing for everything else. So we can see that there's here a Mellanox dual 10 gig network card, which is connected to the second CPU. You can see it's currently link detected is true, and it's negotiated at 100 gigabits per second. Then there's a secondary card here, which is actually the second port of the same card. So it's obviously on the same NUMA node. Then again, I'm saying obviously, but it can be harder than that. Mellanox actually pulled a pretty funny trick some few years back, I think, where they've got something, I think it's called a sidecar or something like that, which is effectively a second small PCIe device that comes with your network card that you can put in a different slot on purpose in a different NUMA node. which then has I think a fancy kind of ribbon cable that connects from that second slot to the card on the first slot, and that actually makes it possible for your card to be on both NUMA nodes at the same time. Not only providing more bandwidth, but also limiting that NUMA cost. So effectively, you end up with one port on one NUMA node, the other port on the other NUMA node, but you only have one physical card. So yeah, even though this is two ports, and you would think that both ports would be on the same NUMA node, they don't strictly need to. They did have some SKUs in the past that specifically were not doing that. All right, then there's an Intel, looks like a normal gigabit network card here on NUMA node 0, then a 2.5 gig network card again on NUMA node 0, then another Mellanox card. I think this one is dual 40 gig, and it is on NUMA node 0 still, and then another couple of Intel cards also still on NUMA node 0. So we can see there's actually extremely few things that are currently wired to NUMA node 1. It's basically just the dual 100 gig card. That's actually done on purpose. It's because on this machine, I needed to do some actual testing with the dual 100 gig card. And this is an older machine that doesn't do PCIe Gen 4. So I needed to get as much bandwidth out of the PCIe Gen 3 we could, which meant putting it all on its own and getting as many lanes as possible, which I still think are not actually enough. I think we can run one of the ports that's, I would say maybe 60 gigabit in that config. Or I think it's like both ports are 60 gig or something else. It's not ideal, but it works. Anyway, yeah, this test system, in case it wasn't obvious, is one of the test systems we use for all of the network validation type thing. So it's not very big on the GPU side. It only has a small built-in BMC network card, graphics card, but it's quite loaded as far as on the network side. It also has some variety of storage. That's another thing maybe worth mentioning. NUMA nodes also apply to storage. In this case, we can see that it looks like the SATA controller is on NUMA node 0 because the vast majority of them are all on NUMA node 0. But there's an NVMe drive that is on NUMA node 1. So again, like if this was a production system, I would have done a very bad job at configuring this machine. But given what we're doing with it, it's actually fine. On a production system, you'd want to usually make sure that you have things properly balanced, so that if you've got, if you've got 4 network cards, you want 2 on each NUMA node. If you've got 2 GPUs, you probably want 1 on each NUMA node. Like, you want to try and balance things not only because of the PCIe bandwidth, but also so that you can put workloads on one side or the other and still give them direct access to one of those resources. All right, so that was your intro to NUMA. There's a number of tools and things to actually look at what's going on with NUMA as well. I believe there's a NUMA top command that I don't use that often. I actually find it slightly confusing to look at, but it does kind of show you only suboptimal kind of cases, like when it's going through like when it needs to go across NUMA nodes when it shouldn't, that kind of thing. It's mostly used to really do advanced performance debugging. NUMA stat, I think, is more useful. So it kind of shows you the hit and misses. So effectively giving you an idea of all of the accesses being made on one node or the other, and how many of those needed to cross. So we can see here effectively that currently the stuff I've got running on the first CPU only needed to cross 5,000 something times to the other CPU, whereas the stuff running on the second CPU had to cross 28,000 times. It's still not bad. Like, we're looking at what, 5% on CPU 1, and not even a percent on CPU 0. It's not terrible, but the machine is also not doing anything right now. There are a few knobs within Incus already, so we can probably start with that. So if I just launch a container, let's call it C1. So if I just launch a container, there's not going to be any limit or anything. The processes in there are going to be able to get scheduled wherever the hell they want. That's perfectly fine. And the Linux scheduler will, like, the Linux scheduler is usually, it's NUMA aware. It's not stupid. So it will not reschedule processes back and forth constantly across NUMA nodes, because that would cause their memory to need to be moved or a NUMA hop to access their memory. So in general, the scheduler does a pretty decent job. Like, I don't think our numbers would have gotten much worse, and yeah, they haven't been, by starting that container at all. If we look here, we'll see, yeah, the container is running. It's gonna have access to everything. So if we go inside it and do CPU info, actually I meant to do self start. Okay. So if we look at that, we can see that it's allowed to access all of the CPUs, and it's allowed to access both of the NUMA nodes for the memory. So it's completely up to the scheduler to schedule things on there. And that works pretty well. It's lacking flexibility if you're running with very, very large memory datasets or that kind of stuff, because you don't really get to control which CPU is gonna get on. Like, whatever CPU the process is first gonna start it on is the one that's gonna do the allocations, and therefore the kernel will try to not move it to the other CPU afterwards, because that would come with added costs. That's kind of the logic there. Obviously, you can alter things a bit. So you can go and do limits.cpu, and then you do, let's do 0 through 4, and so we know that through 5 will be the first socket. Let's do the entire first socket, and then actually let's do the wrong thing on purpose. Okay, so if I do that, that container is now pinned to the first 6 cores of each socket, which is not good. It's still not really a huge problem, because again, we're dealing in this case with a container that runs many processes. The scheduler will still do the best job it can on a per process basis, even if this is not as ideal as having pinned only on the first 6 cores of the first socket, or 6 cores and 6 threads of the first socket. The other thing we can see still, the memory is also just 0 through 1. That's fine. I mean, in general, the memory, the scheduler will again try to make the memory line up with the CPUs. So unless you're dealing with VMs, you don't really need to mess with that too much. I'm going to free disconnect. Okay. But the other option we do support. So if I go here, and we unset the CPU limit, we can set another option, which is nodes, and then let's do just nodes 1. So this is going to apply a limit based on the NUMA nodes now. And what did it do? Now I'm kind of confused, because this should have done something. Did it just do it through the CPU set and it's not visible? What's going on? I should have tested that before, but maybe we do have an extra bug here. I'm just checking the config for what that renders as. Probably nothing. Just checking the log too. Did we get an issue? The pin CPUs overrides the NUMA configuration with the CPUs. Okay, but I don't show you one. Yeah, there are no pin CPUs, so why? Might end up actually fixing a bug before really getting to anything here. I'm just gonna stop it, start it back up, and see if we get the same error again. Yeah, we do. That's interesting. So basically what should have happened here is that it should have pinned to just the CPUs within the NUMA nodes selected. So that means NUMA node 1 in this case, so it should have gone with, what was that? 6 through 12? 6 through 11, and then whatever is that, 18 till 23 or something like that. I think it's actually what it shows in the misordered stuff. Yeah, override NUMA configuration with the CPU. So that's what it should have used. And think that's correct. Yeah, that is correct. But instead, it logged that the CPU as if it had a pin to use everything else, which it doesn't. That's the error you would have normally you should have gotten if limits.cpu had been set to the full set of CPU and the nodes were set at the same time. So I guess we're going to start by looking at this one. I was planning on mostly focusing on VMs because I expected containers to behave, but apparently they don't right now. It's not a feature I've really played with before. It's a feature that was added to Lexty at the time, a few months back, I guess probably a year back at this point. And that it seemed like it was working properly, but it isn't. So let's see what's going on. The ping CPU. Okay, I'm gonna spare you from VS Code this time around because I'm gonna need to work on a mix of local and remote system, and it's just gonna be easier if I just do good old-fashioned VI and sending binaries around. So that's the error we're getting. If len CPU is more than 0, then complain. Okay, but oh, okay, I see. It might not actually be wrong then, maybe? Yeah, no, I think it's actually fine. Okay, I see what's going on. So the idea is that the NUMA node pinning is mostly useful if you tell Incus that you want a specific number of CPUs placed somewhere. Because our default is to give you everything, we don't want that particular option to alter that. At least its current implementation does not do that. I tempted to say that this is wrong. I think maybe in the chat some people could comment what they think there, but to me, if I set limits.cpu.node equals 1, I would expect to be tied to that node, which yes means that I'm gonna get half as many CPU cores as I normally would, but I think that's what I would expect. So that might need a small tweak in that logic here, because the current logic is basically look at limits.cpu. If it's empty, then replace the limit, and that's what we can see up here. If it's empty, replace it with the entire CPU set. I don't think that's quite right. I think if it's empty, it needs to be instead set to the NUMA set. I think that would make more sense. Now let me check exactly where we're at in that logic, because this is the background scheduler we have for the CPU, and just want to make sure that I don't break other things by fixing that one. Okay, so we pull the effective CPU list from the C group. That's fine. Then we pass the CPU set. Okay, so that gets us an expanded list of CPU thread IDs, effectively. Okay. Then for that, we go ahead and check and eliminate anything that's specified as an isolated CPU by the kernel. Okay, that's fine. Then we actually compute that back into a normal C group looking string as effective CPUs. Okay, fine, pass this thing, sure. Then we load all the instances. We get the CPU topology, which is needed for NUMA, and that gets us a NUMA node to CPU mapping. So, okay, so that means we've got NUMA node 0, NUMA node 1, whatever, and they've got a map of all the threads within that. One thing here, I'm just wondering, do we have a problem here? I think we do. I think there's a small issue there. Again, I'm pretty much discovering the code as I go. Sorry about that. So what I'm looking at is we're figuring out the NUMA node. Let me check what we do with NUMA node to CPU, because the issue I just noticed here is this is just accessing our resources API. That resources API is not filtered for those CPUs that we mentioned earlier, which are listed as isolated CPUs. And because they're not, that means that we're adding to that set CPUs that should never have anything scheduled on them. So that could be a problem. a question about whether I'm debugging code that I wrote. No, I didn't write that code. So that was something that was given to someone else on the LXD team at the time. Not that this kind of stuff could not happen with my own code. To be fair, like I did write that function, like most of the function, not the NUMA code, but the rest of it, probably as one of the first things that kind of went into LXD all the way back almost 10 years ago. I did a few tweaks to that function since to kind of improve that scheduling logic, but the NUMA stuff was then added by someone else. I did the review, I did some testing, but I never looked into it into too much depth. And now that I need to use it more is when I'm kind of looking at some of the edge cases in there. So yeah, if we ever, so if those tables are only used as basic lookup to know what NUMA node something is on, that should be fine. If they're used as a list of CPU threads that can be used, then they're not good. So let's see, NUMA node to CPU, okay. Then we're pulling, okay, so that's the list of instance. We're figuring out what instances are pinned, which ones are not. Okay, so that's the one that looks at the NUMA nodes. If CPU nodes. Okay, so if it is not empty, we pass the node set. For NUMA node. Okay, so it goes there, NUMA node to CPU. Okay, so we then pull. We do so NUMA CPUs here ends up being the full list of the NUMA the threads assigned to the NUMA node in question. Okay, and then what do we do with NUMA CPUs? Because that's feeling more and more wrong. Okay, so if it's not running, we continue. Otherwise, we apply the default CPU limit. So that bit I still think is wrong, but that's going to be easy to change based on what I just read above. The problem now is the NUMA CPU stuff. What do we do with that exactly? Load balance, okay. So if there is a CPU limit in place as an integer, so a fixed thing, then we will go through the balancing logic, which does fixed based on NUMA. Okay, so it picks from that NUMA set a given number of CPUs. Yeah, it is wrong. Okay, that logic needs to be filtered to remove the isolated stuff for sure. So that definitely needs to be cleared, because at this point we're literally pinning on things we shouldn't be pinning on. Okay, so that will need a fix. That should be a very easy one, mind you, but effectively that is here is wrong. So let's see, how does that work? Isolated CPUs and okay, so that's a simple slice. We can check an ID against. Okay, so we'll just put a note here. Skip any isolated CPU thread, and if that's the new syntax, which I'm not used to yet. Slices contains, I think. Is that it? Yeah, that's the new Go 121, I think, syntax. Okay, and then it's the isolated CPUs in, so it's the slice first and then the actual ID. So in this case, we want thread.id. Oops. Okay, so if this thing is in there, then yeah, just continue. I don't know if the types and stuff is right, so let's just try and build this stuff. Like the reason why nobody noticed that is because isolated CPUs are an extremely bad idea, and most people have moved on from that and don't use the isolated CPU boot flag. So that's fine. Cannot infer. Okay, well, yeah, okay. So I made a typo. That led to a pretty weird error. It's like you can't infer the type, and then the next line is you made a typo in the variable name. So that's interesting. Okay, so that's that particular small bug fixed. That's not the actual issue I'm trying to fix. It's just something I noticed along the lines, along the way there. Okay, so this is fixed. Now the next step is here. The current logic here is if there are no limits, then we assume the limit is all the CPUs. I think this is wrong in the NUMA case. Instead, we should be using all of the CPUs within the NUMA node. So NUMA node to CPU, so actually NUMA CPUs is what we should be using in this scenario. Now, NUMA CPUs is defined here. If CPU nodes, okay. Okay, so that should effectively be changed a tiny bit. If len of, actually no, let's do if CPU nodes is not empty, so then we'll use the other pin, whoops, and so in this case CPU limit become CPU nodes, NUMA CPUs. No. Okay. If restricted to specific NUMA nodes, only use their CPU threads. Okay. And we remember what that logic is meant to do. And I think that's gonna actually make the code behave the way I kind of expected it to. CPU limit, capital L, I suspect. Is that the issue? No. CPU limit, oh, right, here, lowercase l, there we go. Okay, so that should get me a binary. I'm gonna shove it over to the server, and no, it is not. Cannot use NUMA CPUs, variable of type int64 as strings in assignment. Lovely. Okay. Do we have a function that just does the conversion for us? That would sure be convenient. What did we do in the past? So that effective CPUs, how was that generated? Effective CPUs, okay, so that was the initial one, modified one. I thought we altered it afterwards. Oh, here we go. Okay, so just simple strings, but it's a strings. Okay, that's gonna be slightly frustrating. Okay, cool. I just need to generate a separate list that's a string list that I can then join. Okay. So let's do that. So instead of just NUMA CPUs, we're gonna do a separate NUMA CPUs star. So as a string slice, and whenever we play with that, or more likely at the end, yeah, just do it at the end. So once we're done with this stuff, we just go through the entire NUMA CPU. Actually, let's call it NUMA CPU for consistency, and then convert all that stuff to strings. It's a bit annoying, but fine, that will do the job. Also, I don't like the way those variable definitions and stuff are happening here. Let's just clean that up a bit. Okay, that's tripping my OCD a lot less. Cool. Now CPU NUMA CPUs star and NUMA CPUs star format string of this stuff and NUMA CPU. Okay, and that means that here NUMA CPUs star is what I can use. Without chances I didn't make any typo or stuff there. Okay, not good. 521 variable type string. Oh, right. Yeah, this is still wrong. I need to actually do a strings dot join of this thing, comma separated. Okay, this time I'm gonna get it right at some point, you know. Okay, so that built, sweet. Just making sure formatting and everything is fine. Yeah, it is. I'm just gonna shove that over to my test machine and see if it works before actually making some commits for that stuff. So actually, let me just move things around a tiny bit here. There we go. Ubuntu on lab machine. Go, and then on there, move the Incus D over my main system one and restart Incus. And now in theory, restarting that particular container, just rechecking its config. I'm not sure what it's like right now. Okay, yeah, it's good. So it just pins to the second NUMA node. So let's just restart it. Okay, let's look at the log. It shouldn't complain too much more, hopefully. Like, it's got a bunch of complaints from earlier. The pinned CPUs, override the NUMA configuration with the CPUs. Okay, but are the two the same ones now? Yeah, they are. Okay, so the error is still wrong, but the logic seems fine. So I need to sort out why we're getting the error at all. Anyway, if I go in there we go, 6 through 11, 18 through 23. So that is correct. That's the entire set for that NUMA node. The memory has not been touched. There's not too much point in messing with that, given the scheduler will do its job. Even though we technically could try and do the right PR cutoffs and that stuff to set the mems allowed list. Okay, so the logic now is functional. The error is wrong, so still need to figure out what's going on with that error because that's not been fixed yet. Okay, so now we are in the pinned case. Sure. Okay, so it effectively says that if you're in the pin case and there are NUMA CPUs, then complain. That's not strictly true. The problem is that comparing to I mean, we could compare the strings. That would be a bit ugly, but that might work. Because the issue right now is that the CPU limit has been overridden effectively. Actually, we can just do it another way. We can just do conf limits.cpu. It's not empty, and we've got NUMA CPUs in place. Then that should be fine. That would mean that if we're no, actually that's still wrong. No, we should never hit that case. No, that should actually be right. Okay, let's try that. Basically, I just want to detect a case where we do have a user set value, which is indeed being overridden because of it's actually overriding the NUMA case. I think that check should do what we want. Let's go ahead and move the binary again and restart it. There. We can also wipe the log for good measure so that we actually have an idea of what's going on in there. Okay, and then restart the instance. Okay. Yay, no more errors. So that's good. Now let's do something else. So if I do limited CPU 2, now that should still be valid. Let's restart for good measure. There shouldn't be any errors. Yep. And doing that, we should be pinned on 2 mostly random threads from that NUMA node. So yeah, 7 and 20, that looks valid. Yeah, that seems fine. But now if we do an actual invalid config, so if I do limit CPU 0 through 2, and then restart, that should actually trigger a bunch of errors. Yep. Okay, cool. So that's working as expected. So if the user does pin on CPUs that are different than the NUMA pinning, then that's going to be complaining. So that's fine. And this is a warning. So the actual pin is still in place, but you're getting a warning that you're not on the NUMA nodes that you asked for. Okay, so that's good. Let's just unset the limit CPU, restart our thing, and we should see it go back to, the full set. Yeah, 6, 11, 12, 18, 23. Cool. All right, so that's good. Let's just slice that up into commits and then look at VMs, because that's what I actually meant to be doing. All right. So first thing is, and where's that logic? It's in Incus D devices. Okay. So Incus D, devices, skip isolated threads from NUMA CPUs. Okay, NP there. Cool. So that. Then the next one is use restrict CPU threads by node. So that's that bit, and technically this bit too. Okay. All right. So that's those two changes. That should take care of the container case and make it behave kind of the way I was expecting it to behave. Now, let's look at VMs, because those need some work. So, VMs. Let's just launch ourselves a basic Ubuntu 2204 VM. Oops, I'm inside the container. Forgot about that. Not sure how many times that happens to me, but definitely does. Okay. So downloading basic Ubuntu 2204 VM image, that's gonna have one CPU, 1 GB RAM, and just be thrown at the scheduler. Like there's no pinning, no nothing out of the box there. And we can actually check how good things are afterwards by looking at the NUMA tooling. Okay, so we do have one CPU, one process running here. I think we can do NUMA start and then the PID. Okay. So here it's showing us the memory assignment, and it shows that we effectively have that it's running on node 1 effectively. So that's where its memory is running on node 1. There's a tiny bit of memory that's coming from node 0, but it's really quite limited. So I think HTOP can actually show us the current CPU something is running on. Let's see, like as in where was it last scheduled? Columns, and we want, where is it? CPU time. Yeah. ID of the CPU. There we go. That's one. So we've got that with F5. Yeah, there we go. So it will show us PID processor. Okay, fine. That should be okay. Let's just go and look at that. Okay. So it shows us, and we can wait a little bit to see it refresh, see if it moves. But so far it's been running on thread ID 10, which if we go look at here, so thread ID 10, this is the core, not the thread of core 4, socket 1. So this is correctly NUMA node 1 for the CPU, memory is on NUMA node 1. Hey, the scheduler has done its job, great. This gets a bit tricky as you give more and more resources. Like the scheduler will probably still do the right thing if we give it, say, limits to the CPU, we give it 4 CPUs. There's pretty decent chance it will still mostly do the right thing there. Let's see. So again, we want this one. This one we're gonna have to change one of the options, which is we actually want to look at the userland threads there. I think there's a way to get like a tree view. Yeah. Is it sorted by page? Yeah, probably not. Okay. My goal is to get the threads for that QEMU process. Where is it? QEMU. Okay. All right. So it's here. We can see the VM running. We can see the different threads. So we've got things on 1, 6, 10, 12, 15, 17, 21. This doesn't feel super well balanced. Like, I mean, we know that 1 and 6, well, 1 is definitely on the first CPU. 6 is just past it, so that's on the second CPU. 12 is back on the first CPU, I believe. So 12, 15, yeah, it's kind of mixed between the two. That's not good. I didn't actually expect it to be bad already. It's also worth noting that not all of those are actual VM processes. Some of them are kind of support IO type processes. So yeah, if we look at the actual memory consumption, it's primarily been allocated onto node 0, which what are the CPU threads for that one? Just want to remind myself. So normally, ideally, we would see the scheduler mostly use the first socket thread. So that would be thread ID 0 through 5 or 12 through 17. And again, if we go look at here, so this one is fine, 0 through 5, so that's not fine. That's not fine. Those are okay. That's okay. That's okay. That's not fine. So yeah, effectively it is not. It's even with just 4 vCPUs, it's not being like adequately pinned, and that probably causes a bunch of crosses, which is not ideal. Let's see if the overall NUMA stat is looking worse. So other node. I'm just looking at the chat quickly. So like we're not seeing a lot of other node accesses. It's likely too that that we're effectively getting lucky so far, and that because the VM is effectively idle, the only real vCPU that's been doing stuff is the first one, and therefore we're not seeing too many crosses between NUMA nodes. But that's still not good. So that's something that we should be trying to fix. Another interesting thing is the VM has 4 CPUs, but the way it's actually exposed to it right now, it just inside the VM, it doesn't know it's across 2 NUMA nodes. It just knows that it's got 4 cores, and that's it. That's kind of on purpose because you're not you're not going like this is a completely flexible config. The scheduler can move you around. We have no idea, and we can't change the topology inside the VM constantly to line up. What is interesting, is if you go and you do, let's do a pin on that VM. So if we apply a pin of 0 through 23, Incus, I'm just gonna fix it. So we'll effectively give it everything here. So that's every single CPU thread on the system. This is gonna work very differently now. We can probably look at that in HTOP, even though the view is going to be a bit more tricky. The way it's actually done is that every one of the vCPU threads are now being pinned very specifically to the different CPUs on the system. So that's why we see workloads on 0, 1, 2, 3, 4, 5, 6, and like every single one of them is hit. That's on purpose because when you do pass a specific pin to Incus, we go ahead and we do that, which has an interesting side effect inside the guest, because now we know exactly where it's going to be running for sure. We can actually expose the correct topology inside of the guest. So if you look at LSCPU in the guest now, the guest does show 2 NUMA nodes. It does show it's got 12 on the first one, 12 on the other. It like really replicates the physical layout. It actually shows that it's got 2 sockets, 6 cores per socket, 2 threads per core. Like the entire topology is fully lined up, which actually allows the guest to then do the proper memory placement and everything itself, which is good. Like the other aspect here, like we do NUMA stat on this process. So there's actually nothing wrong with this particular scenario. If anything, we do the exact right thing. You do see memory allocations going from like kind of 50-50 between nodes. That's also on purpose. In this scenario, we actually allocate half the memory to one node, half the memory to the other node. and the guest is aware of that, so it should never actually end up crossing if a specific pin is in place, and if that pin makes sense. Makes sense here means that it's properly balanced between the two. So if you put a pin that gives 4 cores with their threads from the first CPU and then 2 cores with their threads on the second CPU, this is not a realistic CPU config from what Incus detects. So it will just ignore all of that stuff. It will still do the pinning for you, but the guest is just going to see it as a bunch of individual cores and won't know anything about the topology. But if you pass 4 cores from the first CPU, 4 cores from the second CPU, then it will show you a 2-socket system with 4 cores on each. If you pass 4 cores and their threads on each side, then it will show you the 4 cores and their threads on each side inside the guest. So that's a nice trick we have in Incus, and it works well when you do like very specific pinning. Now, what it doesn't do is actually respect any of the NUMA node stuff. So there are a couple of things that I want to fix. I didn't expect to fix containers first, so that might kind of change my plans for this live stream, because I don't like live streams lasting a lot more than an hour and a half. So we're probably not gonna get to do a whole bunch of fixes in there. I'll probably do a bunch of those afterwards. But the idea here is I should be able to do v1 limits.cpu4 limits.cpu.nodes1. Like, this is a config you can set. It's just not a config that does anything useful. What should happen is we should then extract. So it's still gonna be scheduler managed. The CPU equals 4 just means give me 4 CPUs, don't care which. And the kind of very specific CPU pinning we do for containers is not good, to be fair. It's something we need to do because there are no other mechanisms. A container is a set of processes. It's not a single process. We can't just let the scheduler mess around with it too easily. But for VMs, it's different. For VMs, we want this config to just mean get scheduled on anything you want, so long as it is within that NUMA node. And so it's something that should be reasonably straightforward to actually implement on the like within Incus, by still putting a CPU pin, just not one that's specific to a given CPU, but one that limits it to the entirety of that NUMA node, and then let the scheduler sort it out. So if we go look at the code again for that stuff, so I'm just going here, we go in the instance code. I did do a tiny bit of poking around that earlier to just kind of get an idea of how that stuff worked again. I think it's affinity we want. Yeah, something like that. First sched said something. Set core scheduler. Oh, yeah, there we go. Oh, it was affinity, but lowercase. There we go. Okay. So this is the logic for the CPU pinning. We effectively call a, where's that function? It's a bit earlier, probably. We do have a function that analyzes the CPU set info. So where is that? I guess we call it pretty early on during startup, actually. Okay, so let's just look for CPU info. Okay, get CPU information, and that gets us a struct. That struct includes a bunch of different things. Including, if we go look at the sched stuff again, including if it's not pinned, it's just gonna give us a basic number of vCPUs. So in this case, this is actually the CPU pinning case, because it means, yeah, if the I'm just reminding myself what that stuff was. Okay, so vCPUs are the actual that's the actual map we want from a QEMU vCPU to a specific thread. If this is null, it means that there is no such map in place. So we then just go ahead and put the CPUs in place directly. So that the set CPUs thing, which goes ahead and effectively hot plugs those CPUs into place. Now, if we have a map, what we do is we actually go ahead and set for each one of the process IDs we're getting out of that CPU info call, we go and set a specific map. So in this case, as we can see, we build up a set, unique CPU sets, and the only thing that gets added in there is the single vCPU that the VM uses, and then we go and we apply that to the process ID of that vCPU inside the VM. So that's the idea. That's how that stuff works. Now, what we need to do is do something kind of similar, but for the floating case. So that's for the case. That's for the other case. So the case where we don't have a specific pin in place, so it is not static, but we still want to apply a scheduler affinity, and scheduler affinity here needs to be effectively the entire NUMA node or NUMA nodes if there are more than one set in the config. So that's the general idea. The idea is we need to set up a, instead of a set per PID, as is the case here, we instead need to go and do it like do it on the entirety of the set. So that's the idea. Just need to figure out where the PIDs are coming from. Oh, the other thing we actually do apply, and I'm not sure why there's not a comment here actually. Create a course scheduling group. Yeah. So the other thing we do, there's a mechanism called course scheduling in the Linux kernel, which lets you mark a number of processes as being part of the same group. And if they are part of the same group, it allows for them to be scheduled at the same time on the core end thread of a given CPU core. This is a Spectre mitigation mechanism. So if you use that, it effectively prevents two VMs to be scheduled concurrently on a CPU and thread if they're not the same VM. So that's a mechanism we do by default. We even apply it to containers as well on kernels that support it. So that's one mechanism we do. So the other thing here now is we do the CPU info stuff, which gets us vCPUs. One thing that I'm slightly worried about is this is going to cause hot plug on the platforms that support it, which is fine. But it means that the PID list is incorrect until this has run, because until the CPUs are hot plugged, the PIDs don't exist. So in this case, so just to so hot plug the CPUs on platforms supported, and then here would be where we need to handle NUMA. So handle NUMA restrictions, and basically the idea is we can go ahead and check the config. How do we do that? It's probably expanded config. Limits to CPU.nodes, and okay. So in this scenario, we need to pull a new list of PIDs because we will just have spawned some right a tiny bit earlier. We can actually make that conditional and just do it here. From the hot plug, and then here we want to refresh the PID, the vCPU PID list. Okay, so we're gonna be pulling. That's actually that now makes me wonder if the core scheduling stuff is wrong too. I don't think so, because core scheduling applies to all other threads also spawned, which I'm not sure that is gonna be the case here. It actually really makes me wonder if we shouldn't just reshuffle some of that logic a bit, just to be safe. So instead of doing it here, then do it as a separate step afterwards and refresh, just always refresh the PID list to be safe. Yeah, definitely leaning towards that now, because it's like, again, looking at the code now, I think the core scheduling stuff should be fine, even with our ability to hot plug some CPUs afterwards, but I'd rather be extra sure about that, since that's a potential security feature. All right, so that means we pull the initial bids list, which is primarily used here at that point. So I'm just gonna move that chunk to just where we need it, which is here. And we'll just do it again afterwards for everything else. That's slightly wasteful to do it twice, but I mean, it's a very cheap call, whatever. Okay. Because like in this case here, we don't actually need that information. So always doing it. Kind of hard to. Yeah, okay, fine. So what I'll do is actually keep that logic here. In this scenario, just put the notes that this is hot plug the CPUs, and then refresh the bids list. So in here, we're just gonna go ahead and just straight up refresh this thing. That does mean we call it twice in this scenario only, but that should be all right. Again, that's not really an expensive call to make anyways. And once that's done, then move the core scheduling stuff to happen afterwards when we have the refreshed bids list, so that's safe. And that also means that so now in this scenario is where we would also handle the NUMA stuff. NUMA node restrictions. Pretty much back to what I wrote. I'll just kind of reshuffle that core scheduling thing. Or, expanded config, and here we need the limits .cpu.nodes. So if it's not empty, then here we're gonna have to start passing that stuff. Okay. And for now, we can just kind of make sure that we actually do hit the code that we wanted. So my usual thing is just do its basic debug message, build this stuff, shove it to the server, run it with the NUMA restriction in place, make sure it hits. And then gonna need to just reshuffle some amount of logic, because at that stage, we're gonna need to use this similar parser that what I showed earlier in the scheduler. So effectively building that list of, okay, what are all of the CPU thread IDs for that NUMA node that we can use, and then apply that pin. And again, we're probably gonna want to skip over any of the isolated stuff, to just kind of using similar logic. It's slightly unfortunate it's not the same piece of code doing both, but that CPU set scheduler thing is really kind of container specific, and trying to make it also apply to VMs, that's gonna give me a massive headache. So it's easier to actually duplicate the logic. Okay, so Incus D has been moved, and just restart this thing. Okay. So what's our current config on V1? Limits CPU for nodes 1. Okay, so it does have the case where it should log that it actually wants this. And it did not. Huh. What did I miss? The usual question is like, did I build the binary? Yes. Did I transfer the binary? Yes. Did I move it into place? Yes. Did I restart the thing? I did not restart the thing. Oh well, I will explain it. Okay. So let's restart Incus. And then restart the VM, which this time around should actually hit the code path, hopefully, unless I messed something else up. Okay. Yay! Okay. So where we were expecting, that's all good. Now let's go look at that devices code again. Specifically the NUMA stuff. Okay. There we go. Build a map of CPU nodes to CPU threads. Okay. So that's basically the one we need. We're gonna need the integer version of that. That's good. So effectively need that guy. I might split that one into a separate function later. Like within our device package, I think that would make a lot of sense. So moving this one over to driver QEMU. Yeah, not this one. This one. Okay. So we're just gonna need it here. Just need to remove those that weird Unicode stuff here. And we can just have Go reformat this thing for me, so I don't need to. Okay. And then NUMA. Okay. So back to building a map of NUMA nodes CPUs. It's missing the CPU's topology stuff, so I need to actually pull that. Get the CPU topology. I think it's probably CPU's we've got a resources package with a get CPU function. I think that's what's used for that. Just basic error handling there. I don't know if the resources package is even loaded at that point, so let's see. Okay, it's complaining again, CPUs and okay, yes, because that's, I also need to pull the list of isolated CPUs from what we have here. Yeah, definitely gonna need to do some amount of that. Okay, I mean this one is easy and it's also from the resources package already, so that's good. FG3. Okay. The CPU topology gets the isolated CPU IDs. Okay. Okay. Getting further. Yeah, that built. Sweet. That was easy and unexpected so far. So that does give us the map of NUMA node to potential IDs. And then the next step is I need to actually get from there to actually parsing the nodes for that particular instance. So that's the same logic that we had further down, which is here. So if it says CPU nodes not 0, then we do the resources parse NUMA node set. Okay, and that gets us a list of NUMA node integers, and then we compute a NUMA CPUs. So again, that's pretty much the same logic we want. So copy pasting a bunch of that here, and then remove the bits I don't care. So we don't need a string this time around. We don't need that. We don't need that. We don't need that. What we need is this guy here. That's d.expanded config limits.cpu.nodes. So that's that one. I'm just gonna redo the indent manually on those. Okay, here we go. Okay. Oops. Get the pass the NUMA restriction. This should probably actually go further up in the logic. The error handling is also wrong. In this part of the code, we handle errors that way. So just gonna move that logic at the same towards the top, because it's an easy check to do to validate the value. Okay, so first we bounce the thing, which mostly validates the value in the process, then get the CPU topology, then we get the isolated CPU IDs. We build up a map, a NUMA map based on that, and then we compute the actual NUMA CPUs map from it, which just iterates through the NUMA node set, and then just appends the list over to NUMA CPUs. Okay, so at this point, NUMA CPUs is effectively the pin we need. List of CPU threads for the NUMA nodes. All right, and at this point, we just need to apply it. So that's the part where we need to iterate over all of the PIDs. And the CPU, the set we're effectively building, it's actually kind of interesting. Just checking this guy. So that's the PID, that's the set it's applying to. I don't actually know the semantics for unix.cpu set, because like instead of building this stuff every time, it would probably make sense to have this here actually build up the set. That would make a lot more sense. Just let me open a web browser and go look at what a unix.cpu set looks like. And for anyone wondering, yes, this bit I did write myself, I just don't recall any of it. Okay, CPU set, there we go. So what does that look like? Represents a CPU affinity mask. You can clear a CPU, count, check if it's set, or set it. Okay, so you need to repeatedly call set effectively with an integer for the CPU and then just get added to the set. Okay, so that's fine. We can just do it here. So we'll just build up the set instead of building that. And we just do set.set and we need to actually iterate through that stuff. Hold on. So we need to iterate over NUMA node to CPU for the current NUMA node. Okay. Okay, so now we get the ID and we just need to add that to the set. I'm pretty sure it's going to be mad at me about the type because I would guess that we're returning N64s or UN64s from that API. So we'll just cast it straight back to int and then just do it that way. Okay, so that's going to get us our set. And once we do have the set, we don't need to do that logic anymore. We just need to iterate through all of the process and then straight up apply the set to them. And in theory, we're done. Now, what are the chances that this thing actually builds? Probably not very high. Okay, that's the only thing that's wrong with it. That's surprising. But apparently it is, so that's cool. Yep. Okay, so then just transfer that over and see if that actually works. Okay. So I moved the binary. This time I'm gonna make sure I actually do restart Incus. I forgot to do that last time. And now I'm gonna be restarting the VM. So let's see if it actually does it. Okay, it did. Let's go. Now the VM is running. And let's go look at what that looks like. So QEMU. Oopsie. So we're pinned on CPU 1, I believe. Okay, what are we looking at? So at some point I'm gonna just remember what CPU is what, but show. Okay, so limit CPUs. We're on node 1 with 4 vCPUs. To be clear, not all of the processes are vCPUs, so not all of them will have been pinned. That's kind of the weird thing there. But that's something to keep in mind. Some of the I/O stuff or some of the background type thing that QEMU does are not going to be part of the pin. That's fine. So not expecting all of them, but we need to at least have 4 of them be on the correct CPU. So that's node 1 again as a reminder. All right. Okay. So we're expecting 0 to 5 or 12 to 17. 0, 5, 12, 17. Okay. QEMU. Oops. Okay. So not good. Good. Not good. 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 Not good. Okay. So how many goods do we have? We've got, and we do see some other rescheduling, which is obviously gonna happen. But it seems plausible this did the trick. Because like this one is wrong. This one is fine. This one is wrong. This one is wrong. Those two are okay. So like we do have 4 that seem fine. I'm just gonna stop this. Actually, what we could do, I should have done that earlier because that would make my life so much easier at this point, is in here actually add a tiny bit of debugging, telling us what are the pins we need to look at. So going to pin those pins. That way the log is going to tell me exactly what pins I should expect to see a pin on, and I can go and look up those specific processes directly, make sure that they do have the pin set, and if they do, then we're good. That's going to be much easier than dealing with a massive list of processes and hoping to figure out a pattern. So let's do that. Transfer the binary. Move this thing. Restart it again. Oops, wrong one. Restart this one. There. Okay. Start the VM. Okay, and look at the logs. There we go. So now we're going somewhere. So now we've got the 4 vCPU processes here. And what that means is we can go and look them up. So 38983 status. And we want, it's like CPUs allowed, I think. Yeah. Okay, we can see there's actually a pin in place, so that's good. And then 39048, same deal. And then 39049, same thing. 39050, same thing. Yay! Okay, so that's working fine, and we can see that they are on 7 through 11 and 18 through 23. So that's respecting the pin, and they are indeed all on node 1. So that's good. And that should mean that if we go look at NUMA start on 388, yeah, there we go. Did I get that one right? No, wrong process. 38979. There we go. Okay, we can see that pretty much everything is on node 1 as expected. So yay, that works. I'm gonna show you something that won't work, at least it shouldn't, and that's gonna be something I'm gonna be fixing just afterwards. So we support CPU hot plug, and if you don't have a specific pin, then you can totally go and do limits.cpu equals, if I shrink it, that shouldn't be a problem, but if I grow it and I go from, what do we have, 4 now to 5, that 5th one is not going to be pinned. So I'm just going to make sure that we do have all the CPUs. We actually don't, because we need to turn it on. Wherever that is again. Bus system or something? No. CPU, devices, CPU 4, online. Okay, so now we should have 5 CPUs. There we go. So yeah, that fifth one is almost certainly not going to be pinned properly. We can try and figure out which one it is. If we do QEMU, we should see hopefully a process that showed up after the others. Yeah, you can see most of them were created at 1920, and then we've got one at 1922, one at 1923. So we can go look at both, because I'm not actually sure which is which. We actually need the thread ID. That doesn't want to do that now. Anyway, HTOP should maybe be able to tell us that. So yeah, there we go. Spawn time. 39. So those were the same batch. 7, 8, 7, like 47, 48, 49, 50. Those are probably the vCPUs because they're all created at the exact same time, kind of in a row. Those were kind of created later. They're probably some IO type stuff. And so I would guess 39988 is probably the extra vCPU. To be clear, I don't like I can actually figure out for real by poking the QEMU API. I just don't have easy access there. 39988. Yeah. Did I mistype something? 39. Oh, it's a thread. Is that the right syntax now? It's not. Tasks, I think, maybe. No. I hate this. 38979. What wasn't that? Oh, it's not a task. Okay, 39988. There we go. That's the one I want. CPUs allowed list 0 to 23. Okay, so this one is not pinned. So that's kind of expected. It just means that this logic, on top of really needing to split some of it into functions, so I don't need to duplicate that code between both the devices file and the QEMU drivers file. Once I do that, that means I can also call the same logic from both the CPU hot plug case as well as the initial CPU add logic. So that should take care of that. The basic idea is gonna be the same. If we need to pull the CPU restriction and then apply it to the new thread. Because QEMU I don't think gives us the new thread immediately. The most likely thing I'm gonna do is actually a function that just applies it to all of the CPUs, so all of the vCPUs. And so during startup, if NUMA nodes are set, then this is gonna get called, and it's just gonna apply it to all of the vCPUs at that point. And same thing on hot plug. After a hot plug event or hot remove event, we just go and slam the same restriction again on everything just to make sure. The same should probably be done for core scheduling as well, to just make sure that this is also fully enforced on every single new process being spawned. And that's basically it. So that's kind of your look at some of the NUMA stuff. You actually end up seeing a lot more on the container side than I expected to show, as well as how to make this apply to VMs. And then there's going to be one further step I'm going to take is I've been working on some amount of GPU, SIOV type stuff the past few days, and specifically trying to improve what GPUs get selected. So I can actually show you some of that logic. It's in device GPU SIOV, and effectively during startup we do have a bit of logic where that get VF, there we go, which looks like pulls all of the GPUs on the system, applies a basic filter. The basic filter is usually your product ID, your vendor ID, product ID, and then for whatever is left after that, checks whether it supports IOV. If it doesn't, skip it, and then it goes through every single option and looks for this GPU that's currently the least busy. But one restriction that this should also apply is actually actively trying to pick a GPU that's within your NUMA restriction. So that as much as possible, we don't do that whole like going through the other CPU to then access the right PCI device. That's bad. So as much as possible, we want to not only have the VM itself stick to a NUMA node, But if it's restricted to a specific NUMA node, its PCI devices, whenever possible, should also be restricted to that NUMA node. So that's another change I'm going to want to just layer on top of things as part of this change. And that's it. That's probably way more than anyone really wanted to ever hear about. NUMA, memory, PCI, and all of that stuff works, and how you apply pins and all that kind of stuff. But that probably showed you also a bit of a behind-the-scenes look at how we do all of the CPU handling within Incus, including some of the weirder stuff like the C group CPU set, the syntax that we need to respect to set those things, how you apply it to live processes for like VMs, and also some of the small oddities like around things like isolated CPUs. That's mostly not been a thing for a while, but we still need to kind of keep in mind and try and respect. All right, so that's it. Like got quite a bit of work on Incus coming up, and yeah, that's it. Hope you enjoyed that, and I'll see you in the next one. Bye.